My name is Alayna Willitzer, and as a biomedical engineer, it is important to understand what materials are biocompatible. For a material to be biocompatible, it has to be non-carcinogenic, so it can't cause cancer, is non-corrosive, non-toxic, and there is no inflammatory response. With these criteria met, this means that the material will not cause harm to the tissue in our body. One material being researched to see if it's biocompatible or not, or is just being researched in general, is the single-wall carbon nanotubes. So they were discovered in 1991 during an experiment that was using fullerenes. Fullerenes are a cluster of carbons that are single bonded and double bonded together to create this ball formation, which is why they are known as buckyballs. So in this experiment, the product was found to be the single wall carbon nanotubes, which are now heavily researched today and have been found to be used for drug delivery, increase energy storage, and can utilize hydrogen as a fuel source. But before actually being able to get into these applications, the structure of the single wall carbon nanotubes needs to be understood. So when you look at the molecule, the atoms are covalently bonded together, which means the electrons are shared rather than being transferred. So the overall structure is a hexagonal tube. It is almost similar in a way to graphene, except graphene is a sheet. Now, the atoms are arranged in a way that is similar to the hexagonal closed package, which is a type of crystal structure. There are three different types of crystal structures. They are the body-centered cubic and face-centered cubic, along with the hexagonal closed package. By looking at the overall structure of the molecule, it is easy to determine what types of mechanical properties the single-wall carbon nanotubes may have. So one of the properties that scientists have researched is the melting temperature, which is 3,550 degrees Celsius, which is considerably high because the molecules within the single-wall carbon nanotubes don't want to break apart because they're so stable. Another property is the hardness, which hardness is defined as a material's resistance to deformation. Now this is 25 gigapascals within the single-wall carbon nanotubes, and when you compare this to aluminum and steel, it falls within the range, so it's not higher or lower than either one of those. A third property is Young's modulus, which is a material's resistance to elastic deformation, which for the single-wall carbon nanotubes is 1.71 terapascal, which is a significant difference between steel, which is the 250 gigapascal. Now, before any testing can be done, there has to be a way to create them, and there are three methods known to create the single-wall carbon nanotubes. There's the laser ablation, carbon arc discharge, and the chemical vapor deposition. Now, all three of these methods require high temperatures and a metal catalyst. The metal catalyst will help create a more selective product because without the metal catalyst, you can create the multi-wall carbon nanotubes rather than the single-wall carbon nanotube. In the laser ablation method, a quartz tube is filled with graphite and the metal catalyst, and then the CO2 laser is pointed at the tube. Now the laser has a temperature of 1,200 degrees Celsius, and because of the high temperatures, the graphite is then evaporated while the CO2 gets absorbed into the molecule. This produces a plasmic product. However, you can get different states of matter for the product, so if there's less flux within the laser, this means there's going to be a more gaseous product that is formed. So the second method to creating single-wall carbon nanotubes is carbon arc discharge, which in this method it uses electrodes, a noble gas, a carbon gas, and a metal catalyst. So the cathode and anode are placed into a chamber. A direct current is sent through the chamber, and with the high temperatures of about 1,200 degrees Celsius, this creates a pressure buildup, and this then produces the carbon soot that lines along the chamber and on the cathode. Now, when the carbon soot is collected, it does need to go into a final examination because the multi-wall carbon nanotubes ends up being a side product. It's not going to be much because the metal catalyst was used, but there's still going to be some of the multi-wall carbon nanotubes visible within the product. The third method to creating the single-wall carbon nanotubes is chemical vapor deposition. So in this process, it utilizes the nanotubes' ability to expand on surfaces. So with this, holes are drilled into a silicone tube. They're then filled with the metal catalyst in nanoparticle form, and then a hydrocarbon, typically acetylene. Now, when temperature reaches 700 degrees Celsius, acetylene will break down and then react with the metal catalyst. The reactants will then solidify, creating the product, and as the product it forms in the designated shape of the tube. After the creation process of the single-wall carbon nanotubes, a purification process is put into place. Even though there is a 90% yield, there are still unwanted chemicals that bring down the purity of the single-wall carbon nanotubes. So the graphite particles are first removed, and then it's the metal catalyst, and then finally it'll be the larger carbon clusters. Now, this will be different for each creation method, but it's the same process. It just requires different chemicals. Now with the purification process, it lowers the yield, but it ultimately improves the purity. So after understanding the mechanical properties and then the structural information of the single-wall carbon nanotubes, real-world applications are able to be studied. So single-wall carbon nanotubes are being added into batteries. This improves the energy storage, and then it also creates a longer-lasting battery. Sherwin-Williams is also using their single-wall carbon nanotubes. What they're doing is they're placing it inside the epoxy. They're placing it inside the resin, and then this creates a longer-lasting epoxy coating resin. So then the single-wall carbon nanotubes are also being used to create hydrogen as a fuel source. So what happens is the capillary effect within the single-wall carbon nanotubes is utilized, which this condenses the gas, which makes it a higher density without actually turning it into the liquid phase. So hydrogen, being more abundant within the molecule, can be stored at a higher density and then used as a fuel source. The final application is drug delivery. Now, since the single-wall carbon nanotubes are able to move through the cytoplasm, this means that the healthy cells will not die off when cancer patients take their chemo drugs. So when cancer patients take regular chemo drugs, what happens is all of these cells are hit, not just the cancerous cells, but all of it. And with the single-wall carbon nanotubes, it makes it more selective to just the cancerous cells. Even though the applications are beneficial, there are still safety factors that need to be taken into consideration. So because of their smaller size, this means they have a higher toxicity, and the single-wall carbon nanotubes are more reactive. It also doesn't help that scientists need to be able to research and find out more information on the single-wall carbon nanotubes, and because there is still so much that is unknown, scientists are unsure of how they may impact the environment and the people. This is why the applications are still going through the research phase. Now, even though there are these safety factors, there is more good that comes out of the single-wall carbon nanotubes than bad. So in the end, the good outweighs the bad.